Next we will going to construct a MP test for testing h naught theta equal to theta naught versus h1 theta equal to theta 1 in the case of exponential. Okay, here the question is given a random sample of size n from exponential with the parameter theta distribution. Construct most powerful test for testing h naught theta equal to theta naught versus h1 theta equal to theta 1. Case 1 is theta 1 is greater than 0 and case 2 is theta 1 is less than 0. Okay, we will construct the MP test. So here we know that x follows exponential with parameter theta, right? Then under h naught the likelihood function is, what is that likelihood function? Under h naught the likelihood function is equal to L theta naught x equal to theta naught power n e power minus summation xi into theta naught, right? Here I from 1 to n. And what is under h1 the likelihood function, that is L theta 1 x equal to theta 1 power n e power minus summation xi theta 1, right? I from 1 to n. So we know that we reject h0 for the large ratio, right? For that we have to take the ratio is likelihood under h1 likelihood under h0, right? Which is greater than k1 value. So here we will substitute the value of likelihood, then we can get likelihood under h1, that is theta 1 power n e power minus summation xi theta 1 I from 1 to n divided by likelihood under h0, that is theta naught power n e power minus summation xi theta naught, right? I from 1 to n, which is greater than k1. We can write this term as theta 1 divided by theta naught power n. We can write these two terms, that term together, right? That is e power minus summation xi I 1 to n, then theta 1 minus theta naught, right? This is greater than k1. So here we need the function of random variable, right? Here the function of random variable is summation xi, right? So we need that term which is greater than 0, greater than k or less than k, right? So for that we will divide by this term. Okay, that is minus summation xi theta 1 minus theta naught, which is greater than k1 divided by theta 1 divided by theta naught power n. Okay, this implies e power minus summation xi theta 1 divided by theta naught is greater than k2. Okay, here k2 equal to k1 divided by theta 1 by theta naught power n, right? So here we need summation xi, right? For that we have to take log on both sides, right? Take log on both sides, then which implies that log of e power summation minus summation xi theta 1 minus theta naught is minus summation xi theta 1 minus theta naught, right? Which is greater than k3. Here k3 equal to log k2, right? Here we need only the summation xi term, right? So here extra is minus into theta 1 minus theta naught, right? Here in the case 1 is theta 1 is greater than theta naught, right? Then what is theta 1 minus theta naught is greater than 0, right? In the rejection region, we know that it's the term, right? That is summation minus summation xi, that is I from 1 to n, theta 1 minus theta naught is greater than k3, right? Here this term is greater than 0, right? But here one extra minus 1, right? That is minus sign. So minus into negative into positive is a negative, right? Then which implies summation xi. If we divide by that term, then the sign changes, right? That is k3 divided by minus theta 1 minus theta naught, right? That is here I 1 to n, which implies summation xi I 1 to n, which is less than k. Then test for testing null hypothesis versus alternative is phi of summation I 1 to n xi equal to 1 if summation xi is less than k, right? 0 otherwise. Here we can use a non-randomized test, right? Because the exponential is a continuous distribution, right? Then here we need to find out what is the value of k. That is to determine k, we can use the size of the test, right? That is expectation of phi of summation xi equal to alpha, right? Here which implies the p probability of summation xi less than k plus 0, right? Summation xi less than k plus 0 equal to alpha, right? I from 1 to n. So here we know that x follows a exponential with parameter theta, right? Then what is 2 into summation xi divided by 1 by theta? This follows chi-square with 2 degrees of freedom, right? So we make a transformation here, some changes, that is probability of 2 into summation xi I 1 to n divided by 1 by theta naught, right, is less than 2 into k divided by 2 into k divided by 1 by theta naught, which is equal to alpha, right? Which implies what is this term? Then probability of this is chi-square, right? Chi-square with 2n degrees of freedom, which is less than 2k theta naught equal to alpha, right? So here probability of some term is random variable is less than some value, right? So here we need to make a greater than. For that 1 minus probability of chi-square 2n less than 2 theta naught k is equal to 1 minus alpha, okay? Then which implies probability of chi-square 2n, here 1 minus probability of chi-square 2n less than 2 theta naught k. You can write that term as the probability of chi-square 2n degrees of freedom, which is greater than equal to 2 theta naught into k, which is equal to 1 minus alpha, right? From here we need to find out what is the value of k, right? Then if then k equal to, what is that k? K equal to here 2, then we can write 2 theta naught k equal to, what's that? 2 theta naught k equal to 1 minus 2 theta here. Here we need to find out k, right? So that 2 theta naught k equal to chi-square 2n degrees of freedom 2n comma 1 minus alpha degrees of freedom, right? So 2 theta naught k equal to chi-square 2n 1 minus alpha. It's like the last in the case of size test, right? We done the similar procedure, right? This here 2 theta naught k equal to chi square 2n 1 minus alpha degrees of freedom, then which implies k equal to chi square 2n 1 minus alpha divided by 2 theta naught is a value of k, right? So here we also want to find out the power of the test, right? Then what is power of the test? Power of the test is expectation of phi of summation xi I from 1 to n under alternative hypothesis, right? Which implies probability of summation xi is less than k under alternative hypothesis, right? Which implies we can make here also the transformation, that is a xi to summation xi to chi square, right? That is a probability of 2 summation xi into theta 1, right, under h1, which is greater than 2 theta 1 into k, right? Which implies probability of here this is chi square to n, right, which is less than theta 1. What is the other 2 theta 1? Then what is the value of k? K is chi square 2n 1 minus alpha divided by 2 theta naught, right? Which implies the probability of chi square 2n, which is less than 2 get cancelled, that is theta 1 divided by theta naught chi square 2n minus 2n 1 minus alpha degrees of freedom. This is the power of the test. In the case theta 1 is greater than theta naught. Okay, then we go for the second case, that is case 2. Theta 1 is less than theta naught. This is your homework. Okay, then you will go for another question. This is your homework. Then we will go for the another question. Okay, and the question is given a random sample of size n equal to 1, size n equal to 1 under h naught, x follows under h naught, x follows uniform with 1 comma 0 versus h1, x follows exponential with the parameter 1. Okay, then construct most powerful test for testing h naught versus h1. So here the question is given a random sample of size 1 under h naught. H naught is x follows uniform 0 comma 1 versus h1, x follows exponential 1, and construct MP test for testing h naught versus h1. Okay, so here is a case of size 1, right? And here it also mentioned the 2 distribution, that is under h naught x follows this random variable, one single random variable, right? Here n equal to 1, that is a single random variable. So that random variable for here x is in alternative hypothesis, it says that x follows that random variable follows exponential with parameter 1, and an alternative says that, sorry, in null hypothesis says that random variable follows uniform 0 comma 1 distribution. Okay, here we need to construct the MP test for testing these h naught versus h1. Okay, so we will construct the test. and solution here under h naught under h naught. Here one single random variables, right? So here we can take the density f naught of x equal to, under h naught he says that x follows uniform 0 comma 1, right? Then what is the density for uniform 0 comma 1? That is 1 if 0 less than x less than 1, right? 0 otherwise, that is 0 x is greater than 1, right? This is the density for uniform 0 comma 1. 1 if 0 less than x less than 1, because here 0 and 1, right? Then 0x is greater than 1. Then what is the under h1? X follows exponential 1, right? That is under h1, under h1 f1 of x equal to, what is the density for exponential? If parameter is theta, then x follows the exponential with parameter theta, then f of x equal to theta e power minus x theta. X is greater than 0, right? But here in the question it says that x follows exponential with parameter 1, right? Instead of theta, here we need to substitute, we need to write 1, right? That is a f1 of x e power 1 into e power minus x, right? If x is greater than 0, right? 0 otherwise. So from the Neyman-Pearson lemma, we reject h naught for the large ratio, right? So for that we have to take the ratio between f1 of x divided by f naught of x, right? But here in f naught of x, the ranges are 0 less than x less than 1 and x is greater than 1, right? So here if we take the ratio between x for f1 of x divided by f naught of x, it's difficult, right? Because the ranges are changed. Here range is 0 less than x less than 1 and x is greater than 1. But in the case of f1 of x, the range is x is greater than 1, 0 otherwise, right? So for that we have to make these ranges, these we make change this range, right? We can write this range as f1 of x e power minus x if 0 less than x less than 1, same, right? X is greater than 0, right? So we can write this term also. Then e power minus x if x is greater than 0, right? Here 0 to 1, right? Same. Then here same, right? f1 of x takes the value e power minus x when x is greater than 1, right? Then 0 otherwise, right? Because here we need to write the range is this type, because here f naught of x is range is like that, right? That is 0 to 1, x is greater than 1. So taking the ratio, we have to write the ranges same. Is it clear? This x is greater than 0 is a similar, like x is greater than 0, then take the value same, right? Here also, here 0 otherwise. Then from Neyman-Pearson lemma, we reject h naught if f1 of x divided by f naught of x is greater than k, because here in last problems we are taking likelihood function, right? Because in the question it's given that a size of n, but here in this question is given the sample size is 1, so we have to take the density only. Okay, so here This is for the single variable. There is f1 of x divided by f0 of x. Right? This is greater than k. Then we can reject the null hypothesis. So what is the value when f1 of x divided by f0 of x? Okay. f1 of x divided by f0 of x. So have to take the ratio, right? Here we know that what is f1 of x? It is e power minus x divided by the range same, that is 1, 0 to x. Here 0 to 1, sorry, 0 to 1, right? That is 1 if 0 less than x less than 1. And second, e power minus x if x is greater than 1. Then here, in this case, x is greater than 1, f0 of x is 0, right? It is divided by 0. Then 0 otherwise, right? So what is the value when f e power minus x divided by 0? That is infinite. Okay. So here, this is the ratio, that is f1 of x divided by f0 of x. So how to find out what is the value and what is the rejection region? So we know that we reject for the large ratio, right? Here this is a large ratio, right? Because it is infinite. But in this case, we have to find it for which value, which is the largest value, right? For that we will draw a graph. Okay, so here 0, this is a x value, this is f1 of x divided by f0 of x ratio. So this is a increasing function or decreasing function. f1 of x, e power minus 6 is a decreasing function, right? Until 1. If x takes the value 0 to 1, it's a decreasing function, right? Because e power minus x is a decreasing function when x takes the value 0 to 1, right? So here 0 to 1 is a decreasing function, right? So we reject a h0 for the large ratio, right? So here we will take this is a large ratio, right? According to e power minus this value, e power minus x, this is a larger, right? Larger ratio. We can take as a some k value. Okay. Then we also know that after x is greater than 1, it's take the value infinite, right? 1 to here x is greater than 1, which means here this value, that is to infinite. Okay, it takes the value infinite. It take this is a infinite value. Okay, for the that is we reject h0 for the x is x value is less than k. Okay, x value is less than k, that is for the large ratio, and also or x takes the value greater than 1, right? This is infinite value in this region. Okay, what is the rejection region is x is less than k or x is greater than 1, right? X takes the value less than k, then it's maximum, right? Or x is greater than 1, it is infinite value, right? Then what is test function? Then test function is phi of x equal to, here phi of x, right? Because single variable, phi of x equal to 1 if x is less than k or x is greater than 1, right? That is here x is less than k means 0 less than x less than k, right? 0 less than x less than k, right? And x is greater than 1, which means 1 less than x less than infinite, right? This value, from these, for this value the ratio is maximum, right? That is 1 less than x less than infinite, right? Then here the test function 0 otherwise. Then here we need to find out the size of the test and also power of the test, right, using this test function. That is what is size of the test? Size of the test equal to expectation of phi of x under h naught equal to alpha, right? Which implies probability of here 1 into probability of x less than k or x greater than 1, right? This probability of 1 into x less than k or x greater than k equal to alpha, right? Which implies probability of x less than k. We can write these probability of x less than k or x greater than 1 as probability of x less than k plus probability of x greater than 1 equal to alpha. Okay, so here it's under h naught, right? Size is calculated under h naught, right? Expectation of phi of x equal to alpha under h naught. Here probability of x is greater than 1 under h naught. Here we know that probability of x is greater than 1 is equal to 0, right? Under h naught probability of x is greater than 1 is 0, right? So then this term is 0, and then which implies probability of x less than k equal to alpha. So here we need to find out what is the alpha, right? It is a probability of x less than k integral over but 0 to k f naught of x under h naught, right? That is f naught of x dx equal to alpha, which implies what is the f naught of a when x is less than k? Integral over 0 to k 1 into dx equal to alpha, right? That is here x 0 to k equal to alpha, right? Which implies k equal to alpha, right? This is the size of the test. And also here we need to find out what is the power of the test, right? That is what is power then? Power of the test. Power of the test, right? That is expectation of phi of x under alternative hypothesis, right? Which implies probability of x is less than k or x is greater than 1 equal to 1, right? So we can write these term as a probability of x less than k plus probability of x, we have 1, right? So x is greater than 1, right, under h1. So under h1 x is great, under h1 x less than k and x is greater than 1. What is x greater than 1 under h1? Under h1 x is greater than k is e power minus x, right? So which implies so here 0 to k f1 of x dx plus integral over 1 to infinite, right? X is greater than 1, so 1 to infinite f1 of x dx, right? Here which implies integral over 0 to k e power minus x dx plus integral over 1 to infinite e power minus x dx, right? And also here we want to integrate this term, right? That is e power minus x minus, right, 0 to k. right? Plus minus e power minus x 1 to infinite, right? It implies here we know that k equal to alpha, right, from the size of the test, right? Here from the size of the test k equal to alpha, right? So here we can write k equal to alpha, that is minus e power minus x 0 to alpha minus e power minus x 1 to infinite, right? Which implies here substitute the values of upper limit and lower limit, then e power minus alpha minus here, okay, then e power minus alpha minus e power minus 0, that is 1, right? E power minus 0 means 1, right? Then minus this term e power minus infinite means of 0, the minus e power minus 1 is e power minus 1, right? Which implies minus e power minus alpha, then plus 1 plus 1, then plus e power minus 1, right? You can write this term as 1 plus e power minus 1 minus e power minus alpha. So this is the power of the test. If alpha equal to 0.05, then what is beta? The substitute value of alpha is 0.05 here, then beta value is 0.4166, which implies beta is greater than alpha, right? From the most powerful test is power is always maximum, right, compared to size.